Hello, and happy June solstice, winter or summer, whichever it may be for you. I'm sitting out here just waiting for the sun to come out again. It's behind a cloud right now, as I've got my setup here for casting a shadow. Hopefully I have properly accounted for magnetic declination with this compass. However, I'm going to see if I can't find true north and also the time of solar noon, maybe without the compass's assistance, because I'm tracking the location of the shadow over time. I've made a couple marks over there already, but as you can see, I've got a tripod here. I've got a camera facing down taking a time-lapse video of the shadow as it tracks, and with a couple inputs of time, I'm hoping that I'm going to be able to model the sun's path so I can pinpoint precisely when the shadow is at its shortest, which would then, by extension, find my true north. This is something that I can do because I have the day off because, well, one, it's Sunday, but two, it's summer and I'm a teacher, so I'm not teaching today. I can't do this with my students, though, because school's out for summer. But if I do this again, there we go, on the September equinox or the March equinox, I can find my latitude from the equator, which is, well, your latitude. Anyway, it looks like I've got a shadow out. My clock says it's 12:06, so I'm going to mark that location and then let the camera do its work. Well, this has been going for about an hour and a half before solar noon, now to about an hour and a half after solar noon. The camera looking down overhead should give me enough data points to build a model of where the shadow was at any given time so that I should be able to work out exactly when solar noon occurred, even if there wasn't a shadow at that time. Okay, so now that the experiment has been performed, it's time to process the data and produce a model. And so the first step there would be to actually import the data, which is this. This is just an image taken from the overhead camera's point of view. I've rotated the image so that my expectation of true north is aligned with the y-axis, and I've set it up so that the source of the shadow is essentially at the origin. And so hopefully that should simplify the mathematics. And as you can see, I've got a clear view of all these points that I had marked with chalk, including the time. That's essentially my data. And so the first step is to just import those as points, right? So I've matched these points to the locations of the end of the shadow at certain times. I've labeled them with the times at which they were recorded. And now from this, we can produce a regression. And, obviously outside of these data points, it doesn't really matter what's going on. What matters is that it resembles it close by. And so with this, I should be able to interpolate where the shadow would have been at any particular given time. In fact, the timing is kind of important here because there's not a linear relationship between when the shadow was and where the shadow was. As the sun climbs higher in the sky, the position of the shadow changes more slowly. So I also took the time, I essentially just converted it into minutes since 1147. And then the x coordinate of this point, and I made a separate set of points with its own regression so that I should be able to model where the shadow should be at a particular time. And so if I move back in here, I've got this function, this regression, which models the path of the shadow, at least during this 3-hour period, and also this blue function, which is modeling when or how many minutes since 1147 the shadow had moved horizontally across my picture. The last little bit of information has to do with the most important time in this experiment, which is solar noon. Now, the expectation is that solar noon would occur when the shadow is pointed directly towards my hemisphere's geographic pole. In my case, that's the North Pole, and that would correspond to essentially the y-intercept. However, it's also supposed to correspond to when the shadow is the shortest. So if you take an expression for the distance between the origin and this function and minimize it, I actually end up with a slightly different point, just to the left of the y-axis. Hopefully you're able to see that. It occurs very slightly to the left. Of course, this could be an issue with my data points and the regression, but it could also just be that I had an error with reading where north was. The compass sometimes isn't exactly reliable. That's only off by a little bit, but because I have a regression that relates where the shadow is to when the shadow is, I can also find when this x-coordinate occurs, and that happens at 85 minutes after 1147, which is actually 1:12 p.m. Now, 1:12 p.m. is not the exact time that the solar noon calculator predicted my solar noon would be. That's off by about 4.5 minutes, but honestly, that's pretty good. So the very last thing to do here, right? Because a model is only as good as its ability to agree with the real world data, right? So I do have these 1, 2, 3, 4, 5, 6, 7 marked points, but I also have a 3-hour long video. And I want to make sure that if I were to synchronize this model's prediction of where the shadow should be with the video of where the shadow actually was, they would match each other. So I've taken essentially just a segment that connects the origin to a point along this regression, and I've fed this blue regression into it so that this will move across the shadow quickly when it should be quickly, slowly when it should be slowly. And if this model, let me just animate this variable, if this model is a reliable or accurate representation of what actually happened, if I were to take just that moving red line, it should follow the shadow in the actual video. So let's see that. So now that we know that this is a reliable model, we can use it to draw some other strong conclusions. For example, I did measure the lengths of a couple of the shadows earlier on, and if we compare those to the lengths of the segments in the model, then proportionally we can work out the length of any particular shadow at any given time, including the one at solar noon. If we work out what my latitude is from that shadow length, turns out that I'm a little bit more than 15 degrees north of the Tropic of Cancer, which actually works out to less than a degree off from what Google Maps says my actual latitude is. So these two vital pieces of information, what is my latitude and what time did my solar noon occur, again, in my experiment that turned out to be 1:12 p.m., they're all I need to be able to contribute to participate in the measure project. If I and another experimenter sufficiently far away that their data is, actually kind of different from mine, then we can combine those to calculate Earth's radius. The more people that participate and submit their data, the better our statistical analysis would be. The next time that we can perform this experiment is actually in September. It's going to be the September equinox, Tuesday, September 22nd, 2026. And whether you need to do it the day before or day after for weather or for scheduling, it's still good. I want to see as much participation as possible, because the more people who participate, the better the data is. We can actually perform an experiment using rudimentary tools, be as sophisticated and clever or as bare bones, as simple as you would like, or as your class needs to be, whether you're a teacher or a student, or even if you're just an enthusiast who wants to do this for themselves in their own backyard. I'd love to see your participation this fall. I'll see you then.